Welcome back. In this lesson I'm going to introduce the concept of Monte Carlo burnup simulations. In order to account for fuel depletion, the time is introduced into Monte Carlo burnup simulations. When the fuel is being depleted in a nuclear reactor, the atomic concentrations of various nuclides change. Some nuclides decrease their concentrations, such as fissile nuclides, for instance uranium-235, but there are other nuclides which will increase their concentration. The fission products will be created during the fission chain reaction, but also some higher actinides will increase the atomic concentrations. So all this will affect the neutron transport in the system. So the atomic concentrations of various nuclides are affected, and this will affect the total macroscopic cross-sections of different materials in the system. Since the total macroscopic cross-sections are changing over the time, we know that also the fission source distribution and therefore the power distribution in the system also change over the time. So for instance, at the beginning the power distribution may look like this in a slab reactor, but after a certain amount of time the power will change. Now how it will change? You can see that at the beginning most of the neutron flux was located in the center of the slab. Therefore the fuel will be depleted at the largest rate in the center. Therefore the amount of the fissile material in the center will be dropping faster than at the locations which are close to the boundaries of the system. And because of this, the fission source distribution and the power distribution will get flattened over the time period. So after a certain amount of time, the distribution may look like this. The flattening of the power distribution may not be entirely caused only by the decrease in the atomic concentration of some fissile nuclides, but it may be also due to the introduction of some fission products like xenon-135, which has a very large cross-section for thermal neutrons. So especially the thermal systems are very sensitive to xenon-135. So in the locations in which the power distribution is very large, more xenon-135 is being generated there. Therefore more neutrons are being captured in the xenon-135, and that will remove the neutrons from the system. So this effect also contributes to the flattening of the power distribution. So you want to capture all these processes in the Monte Carlo burnup simulations. So we want to calculate the evolution of the power distribution, the fission source distribution, the excess of reactivity, and all other possible results that we want to know over the whole time period. Now, in order to build up a foundation for the Monte Carlo burnup simulations, let me introduce two quantities: the nuclide field and the neutron flux. So all these quantities are dependent on the position in the system and time. The neutron flux is also dependent on the energy. As you can see, the nuclide field is a vector. Let me write it down here. The elements of the nuclide field vector represent atomic concentrations of different nuclides. It doesn't really matter how they are sorted in the nuclide field vector. It's up to us, so we can choose the order. So for instance, the first element may represent the atomic concentration of hydrogen 1, and this concentration is dependent on the location in the system and time, right? The second element may be, for instance, deuterium, so that's hydrogen 2. Again, it's dependent on the location and time, and so on. And then we can have atomic concentration of xenon 135, and one of the elements will represent the atomic concentration of uranium 235. And then the higher actinides can follow. Let's have a look at the neutron flux quantity. The neutron flux is defined as the product of the neutron concentration n and velocity. Let's try to figure out the unit of the neutron flux. So let's have a look at the product of the neutron concentration and the velocity. The unit for the concentration of neutrons is 1 over cubic centimeter, and the unit for the velocity is centimeter per second. So that will combine into the unit 1 over square centimeter per second. Now from this unit we can already derive one interpretation of the neutron flux as the number of neutrons passing through the unit distance per second. But that is not the most practical interpretation of the neutron flux physical meaning. There is another one which actually you can get from the unit which we write in this form, and that will be the distance that the neutrons which have the velocity v travel in a unit volume per second. So it's a combined distance that all the neutrons that have the velocity v travel in a unit volume per 1 second. And that actually makes it very easy for us to calculate the neutron flux in Monte Carlo simulation, because as we simulate the neutron transport, we can easily calculate the distance that the neutrons travel between the collisions. We can just combine these distances within the volumes in which we measure the neutron flux. Now, for the purpose of the Burnup simulations, we actually need neutron flux which is integrated over all the neutron energies. Therefore, we calculate the distance of all the neutrons, of all the energies that travel within the volume that we monitor. So we can easily calculate the neutron flux distribution in the system by the Monte Carlo simulation. As for the nuclide field, we need to calculate it using the Burnup equation. And the Burnup equation is written right here. As you can see, the Burnup equation represents the time change in the nuclide field vector. the change is given by the product of this matrix M, we can call it transmutation matrix, and the nuclide field vector N. The elements in the matrix represent rates at which specific nuclides are being transmuted into other nuclides. So for instance, if we take the matrix element Mij, that would represent the rate at which the nuclide J would be transmuting into nuclide I. Now the transmutation matrix is formally defined by this formula here, in which you can see two other matrices. The matrix X, which is the cross-section and yield matrix, and the matrix D, which is the decaying matrix. And you can see also the neutron flux in it. So the product of the neutron flux and the cross-section and the yield matrix give us the transmutation rates caused by the absorption of neutrons, and the D matrix simply accounts for decay of different nuclides. Now for us it's very important to notice that the transmutation matrix is dependent on the neutron flux. So that is coming from this formula here. So that introduces a dependence of the change, the time change in the nuclide field on the neutron flux distribution. So notice that the Burnup equation is a differential equation. It's an ordinary differential equation. So in principle, solving of this equation requires methods that are designed for ordinary differential equations. Nevertheless, we do know the formal solution for the Burnup equation for one specific case, and that is the case when the neutron flux is fixed in time. Now that is not very practical for us, in fact, because we know that in response to the changes in the nuclide field, the neutron flux itself will change. So because of this, we cannot use this formal solution directly for obtaining the nuclide field at the end of the time period that we want to analyze by our Monte Carlo simulation. However, we can still find some application for this formal solution, as I will explain later. Let's have a look at this formal solution. You can see that it's a product of two quantities, where the first one is the so-called matrix exponential. Let me write the matrix exponential here. So the matrix is in the exponent, and the matrix is multiplied by the time interval, time minus the initial time 0. And you need to understand that the matrix exponential is a matrix. This is a matrix. The whole thing is a matrix. So here, this formal solution is a product of a matrix and the nuclide field at time t0, the initial time. So we are going to have a special solver for obtaining this formal solution to the Burnup equation. So these are called Burnup solvers or fuel depletion solvers, and they always assume that the neutron flux is fixed over a specific time period. and we need to provide the solver with the matrix, the transmutation matrix, and the initial nuclide field at the beginning of the calculation. So in some of the next lessons I'm going to use this solution in this form when I describe different coupling schemes between the Monte Carlo and the fuel depletion solvers. So I'm going to use this as a solution that the fuel depletion solver provides to the Monte Carlo solver. As for the neutron flux solution, I'm going to be writing it in this form by the function mc, which depends on the nuclide field vector. So in some of the next lessons I'm going to describe the coupling schemes. So when you see this mc function, that simply means that we have executed a Monte Carlo solver which returned the neutron flux distribution, neutron flux which depends on different position in the system, and the system was represented by this nuclide field vector, right? So this vector actually can give us the geometry for the whole system, because this vector is dependent on the position in the system. So at every position in the system we know the atomic concentrations of all the nuclides that constitute the system. Now, just for curiosity, I included here the criticality equation. We have seen the criticality equation for the fission source distribution. You may recall it, we have written it as the multiplication factor times the source is equal to the fission matrix times the source. So you can write the criticality equation not only for the fission source but also for the neutron flux, and typically you can see it in this form. On the left hand side of the criticality equation there is the L operator, which accounts for the migration and loss of neutrons, and on the right hand side you can see the F operator, which accounts for the neutron production. Now I can rewrite this equation like this: K times the neutron flux equals the inverse operator to L minus 1, F, and the neutron flux. And now I can combine these two operators into another one. So for instance H prime. Now the H prime operator is not identical to H, because the H prime operator is applied to the neutron flux, while the H operator is applied to the neutron source. So when we apply the H operator to the neutron source, we will get the next generation neutron source. However, when we apply the H prime operator on the neutron flux, we will get the next generation neutron flux. Now I've included the criticality equation for the neutron flux only for curiosity. I just wanted to show you this form, the MC function. When you see it in some of the next lessons, it simply means that this is the neutron flux given by Monte Carlo simulation on a system which is described by the nuclide field vector n. So let me just summarize what we have learned. We have learned that during the Monte Carlo burnup simulations we need to track two quantities. One of them is the neutron flux, which is given by the Monte Carlo solver for a specific system, which is described by the nuclide field vector n. The nuclide field vector, however, is governed by the burnup equation, that gives the time change in the nuclide field vector. And we know the formal solution for the Burnup equation on the condition that the flux is fixed. So we can use this formal solution when we are sure that the neutron flux distribution is not changing considerably during the time period during which we calculate the change in the nuclide field. So the nuclide field vector is dependent on the neutron flux. The neutron flux is dependent on the nuclide field vector. These two quantities are described by two equations. We need two solvers, therefore we need to couple these two solvers together. So we will look at this in some of the next lessons. And that is all. Have a nice day.